Before we talk about exponential growth, we'll look at the basic ideas, which I can talk about by shopping and dining out. Let's say I want to buy a $300 jacket, and it's marked 30% off. If I wanted to do that sort of the long way, I could take 30% of 300, which is $90, and then subtract 90 from $300 and get $210 for the jacket. But that involves multiplying and subtracting. I could do this more efficiently mathematically if I thought about the fact that if I have a $300 jacket and it's marked 30% off, then I really have to pay for 70% of it. I don't worry about the 30% off, I worry about what I'm paying for. Then I go 3 times 7, 21, so that jacket is $210. So when something is marked off, I don't worry about what the mark off is, I worry about what I'm actually going to pay. And I get this number, 70%, by taking 1 minus 0.3. Now, if I look at a dining out question, like let's say I go out to a restaurant and my bill is for $60, and I want to figure out the tip, what I would usually do in my head is, to get a 20% tip, is I would take 10% and I would go 10% of $60 is equal to 6, and then I would double that to get 20%, so that would be 12, and then I would take the 60 plus 12, and $72 would be how much I would pay for dinner. So if I want to think about that more efficiently, what I could do is say, well, I have to pay my entire bill for $60, and I also have to pay a 20% tip. So you can think of this as I'm paying 100% of the bill plus 20% of the bill, and so I'm paying for 1.2 of the bill. And so if I were to take 60 times 1.2, I would get $72. So if you're looking right here, multiplying by 0.7 is more efficient than multiplying by 0.3 and subtracting. If you look right here, multiplying by 1.2 is mathematically more efficient than my whole in my head doubling adding thing. And when we're looking at exponential growth and decay, because it's pre-calculus, we're looking for the most efficient mathematical method, not the easiest one to think about in your head. So let's say I have a town of population in the millions, but we're back in the olden days, maybe in the year 2000, and only 7,000 people have a cell phone. But because cell phones were getting more popular, officials expected that cell phones would grow at a rate of 40% per year. So if this is an exponential growth problem, I would fill in 7,000 for my initial amount, and then 40% per year is the rate. What I fill into the equation is not the rate, but the growth factor. And so the growth factor here would be 1 plus 0.4 to the x. And so my equation for exponential growth would be 7,000 times 1.4 to the x. And you can enter this type of equation in on your calculator and find out how many are in the first year, the second year, the third year, by hitting second table. If you have a graphing calculator at home, try that. And check out how many cell phones you'd have after 1 year or 2 years or 5 years or 10 years. In this example, I buy myself a really fancy $4,000 home theater and sound and everything system. But after I take that home theater system out of the store, I expect its value to go down 12% per year. So in my exponential equation, A is the initial amount, so the 4,000 would go here. But this is like the marked off problem. If it goes down 12%, then after 1 year, it'll still be worth 88% of its value. So in order to work out an exponential decay problem, you need to take the 1 minus the 0.12 to get the decay factor. So this 4,000 is the initial amount, and the 0.88 is the decay factor, and the 12% is the rate of decay. And again, you can check that out on your calculator by typing the equation into y equals and hitting second table, and that will tell you how much that stereo system will be worth after 5 or 10 or 20 years. Another type of exponential decay is a half-life problem. If you have honors chemistry, you've probably already done these questions this year. In a half-life problem, A is still the initial amount, and so when you're filling in the exponential growth, 50 goes in for A. So this would be y is equal to 50. And every 20 days, if the half-life is 20 days, it's saying every 20 days you'd have half as much. So on day 20, you'd have 25 grams of the substance. On day 40, you'd have 12.5 grams of the substance. On day 60, you'd have 6.25 grams of the substance, and so on. And so each time I'm having half as much, so in a half-life problem, B is always a half. But what number goes here is usually confusing to students and a number they often get wrong. So I want you to think about, in any exponential problem, that the number up here, x, is actually the number of cycles. And so the way I think about it is 20 days is 1 cycle, and 40 days is 2 cycles, and 60 days is 3 cycles. And so if I'm going to get this 1, 2, or 3, I can do that by taking 20 days divided by 20 gives me 1, and 40 days divided by 20 gives me 2, and 60 days divided by 20 gives me 3. And so what I'm really doing is I'm taking the number of days divided by 20 days. That gives me the number of cycles. It's the 1, 2, or 3 that goes into the equation. So this is going to be t divided by 20. And so that way, at 20 days, you take a half once. If you're looking right down here at 40 days is a cycle of 2, so if you put in 40 for t, you take a half twice. That's why 40 is 12.5. And if you went to 60 days, for 60 days, you take a half 3 times. That would give you the 6.25. So 60 divided by 20 gives you 3. And so thinking about x as a number of cycles and not just as the variable can help you get half-life problems right. This example is from problem number 23 in your textbook, and it's an example of logistics growth solving an equation. And in a logistics growth problem, A is not the initial amount. A is, and I'm looking at this A right here. A isn't the initial amount. A is how many times more you need to go from the initial amount to the limit. So it's kind of a hard thing to think about, and I want to show you how to think about with the exact example from the book. So the number on top right here, the limit to growth, if you're thinking about a logistics problem, and you remember the shape of a logistics graph, it's kind of going along and then it goes up, and then it goes flat again. This number right here is the limit. It's where it levels off. And so for this problem, the limit to growth is 40. That's saying this question can't get bigger than 40. And so I'm going to put a 40 on top. And then it says the initial value is 10. This could be confusing because the initial value doesn't actually go anywhere in the problem. But you have to compare the initial value to the limit to growth. Here the initial value is 10, my limit to growth is 40, so I think to myself in my head, how many more times I need to go? I would need 3 more 10s to get from 10 to 40. And so the value for a in this equation is 3. And that's times b to the x. And now if I want to solve this equation for b, I need to replace the 20 and put it in for y, and take the 1 and put it in for x, and solve the equation. So now I have 20 equals 40 over 1 plus 3b. If I cross multiply, I end up with 20 plus 60b is equal to 40. If I solve that equation, I get 60b equals 20, and so b is equal to 20/60ths, which is 1/3. And squeezing this thing at the bottom, my answer is y is equal to 40 divided by 1 plus 3 times 1/3 to the x. So logistics problems are also tricky. Logistic problems are tricky because this number right here is not the initial amount. It's how many times more you have to go from the initial value to the limit. Kind of like if you were thinking about the half-life problems, they were tricky because in the half-life problems, the x value, which is right here, isn't actually x, it's x divided by the half-life. So the two tricky things, logistics and exponents.